you. Enjoy. I'll turn the light on. Keep them in so people can see this.
Okay. Jump the gun.
You're getting old too. Men turn up early and sit at the front. What colour car you drive?
I used to see at the front even when I was young. I began those sitting at the back. And then I sat at the front and my my parents didn't realise I was extremely short-sighted. 6 or 7. So I had my first couple of years at school. I just sort of stand in front of everybody like this. To my parents. When do you think you ought to get dog? They thought I was a very affectionate boy. Very close. The cap suggests.
No.
Good afternoon. You've got your own lunch, haven't you?
Yeah, I already got a couple of bits.
Sure.
Yeah, I'm fine. Yeah, thank you.
Do you want to put a plate aside because the vultures will have a lot otherwise?
No, I'm fine.
Sure.
Yeah, thank you. Well,
Sure, I can get you.
I'll get you a
jug pistol.
I'll grab one.
Oh, here.
Actually,
Not have you time.
It's like waiting for the second coming, waiting for that.
thank you.
Bruce here, it wasn't here today. Oh, yes, she did. You grab it, can you?
time, aren't we? Shall we just make a start? Okay. We'll make a start. I think it's probably the time to start. Our speaker today is Mitoulis. Also got the pronunciation wrong. Sturgis is has come to us today from Surrey University, where he's a lecturer at the Department of Civil and Environmental Engineering. And he has been doing research into seismic design. Upstairs, and his talk today is going to be on seismic design of bridges and structures, perhaps. So,
Thank you, Mr. Gibbs. Good afternoon. It's my great pleasure to deliver this lecture at AECOM Construction, since I know they have a broad interest in constructions, bridges, tunnels, and also in earthquake-prone areas. So in this lecture, I will illustrate the research that I have been conducting the last 10 years, almost the last 10 years, during PhD studies and my postdoctoral studies. And I try to keep a contact with practice. I've been working as a consultant engineer in a long highway in Southern Europe. And at the same time, I was attached to an industry that was producing bearings and expansion joints for bridges. So I do have a contact with practice, and I say that I would place myself between the academics and the practitioners. Hence, characterize this lecture as the link between fundamental mechanics, dynamics, and design-oriented research. In the last years, the conceptual design of bridges have been evolving rapidly, especially in seismic-prone areas. And this is due to the fact that bridge engineers may either adopt isolation in order to receive the seismic loading, or integral bridges, which means that pieces are connected rigidly to the deck. In many cases, the abutments are connected rigidly to the deck, and this design concept actually help us to dissipate part of the induced seismic energy through hysteretic behavior, which means that piers respond in an elastic manner. There are parts of bridges, such as the abutments, for example, and the backfill soil, which are developed during earthquakes. And this is what I'll show you today, how two structural parts of bridges can be utilized in order to reduce the seismic movements of the deck, reduce the cost of the bridges, and improve aesthetics, as the piers can be designed with smaller sections, can become slenderer, and foundations which reflect to almost 50% of the final cost of a bridge may also be designed in a cost-effective way. Bridges are vital parts of the lifeline system, and they should maintain emergency mobility and accessibility, not only in circumstances, but also even after severe earthquakes. And imagine what would happen if a bridge would collapse after an earthquake and ambulances don't have access to the hospitals. On-site infrastructure woes take on U.S. economy. This is a Reuters article that was published a couple of years ago, showing the toll place in the U.S. economy due to the deficient bridges, which is an almost $1 trillion problem. In 2010, you can hear the American Society of Civil Engineers card showing that deficient and deteriorating transportation systems, bridges drained $20 billion from the economy in 2000 alone. You can on the top figure the healthy system of the Hakozaki junction. On the left you can see a bridge that has experienced span and seating. You're right, one of the most famous failures on bridges, the Hassi Expressway that was collapsed, that was totally collapsed during the 1995 Kobe earthquake, causing dramatic disruptions of traffic and actually divided the city into two isolated areas after the earthquake. So this global seismic risk, with the red color you can see the areas that do experience large seismic actions. You can see here that is on the west side of America, in the Arab countries, Southern Europe mostly, and in the Southeast Asia. So what exactly is the seismic action? Why do we have to address the seismic issues in bridge design? Action is a horizontal load. In fact, it is an acceleration that is imposed to the structure, and this acceleration is translated into inertial loads. So the structure produces the seismic loads and loads itself by inertial loads. So this is the seismic action, which would not be dangerous at all if we didn't have constructed environment like bridges and buildings. So the seismic design is required for structural design in modern building codes such as Eurocode 8, such as ASTO that is applied in America, Caltrans in California. So bridges are nearly isostatic systems having low redundancy, which means that one failure may lead to collapse. Seismic events can cause catastrophic failures, endanger public safety, and have tremendous impact in economies. I showed before collapse of the Hassin Expressway, and which is related to the impact in the economies. And bridges are vital parts, of course, of the lifeline system that should maintain emergency mobility and accessibility even after severe circumstances such as floods, earthquakes, and extreme wind effects. So that you are acquainted of this project, this is AECOM's project in Hong Kong, was built in 2010. There are many different design concepts that the bridge engineer may use when facing with the problem of the seismic design of bridges. In that case, seismic isolation was used, which means that the deck is supported on the piers and bearings through isolation devices and slides during thermal movements onto piers. The bearings receive this serviceability movement, and as such, the piers are not really loaded during the serviceability limit state of the bridge. During a quake, these devices again receive the large seismic movements and do not transmit seismic loads to the piers. But there are many different design concepts that an engineer may adopt to design a bridge against earthquakes. So let's take the concept design of bridges against earthquake from the beginning. You can see the structural elements of the bridge, the deck and the substructures. The substructures consist of bearings, piers, foundations, and abutments. I have divided this slide into three specific parts. The first part is the structural elements. The second part, with the gray zones, are the design issues. And the third part is the seismic design considerations, I would say. So the deck is usually based on construction methods. The selection of the cross-section has to do with serviceability, stressing, not influenced by seismic actions. We have published in the past a research showing that, in fact, the deck is not affected by seismic actions, not even in bridges with rigid pier-to-deck connections. While at the same time, bearings, one of the most important structural elements of earthquake-resistant bridges, since a bridge relies heavily on their seismic performance. At the time, we have many different types of bearings. There are many companies producing bearings, and in most cases, application and industrial innovation went further than codes and theory. So we have to decide about when we design a bridge, about the right bearings and the correct use of isolation. Piers do participate during earthquake. They either be designed in an elastic manner, which means that they're not expected to exhibit elastic response, or they can be designed in order to dissipate part of the induced seismic energy, which is that high theoretic behavior of the pier is expected during earthquakes. So bridges rely on the pier dissipation, and of course, another design of the seismically isolated bridges piers may lead to the over-design of the foundation, as soon as foundations should have a 4% overstrength as compared to the strength of the piers. What happens to the abutments? The abutments are not utilized in the earthquake-resistant system of the bridge. Due to many serviceability issues, I'm going to show you in the next slide some of these design issues. They're usually designed as if they're retaining structures. No seismic design is applied, even though collision forces of the deck, which oscillates in the longitudinal direction of the bridge mostly, so that may collide on the abutment, and the abutment may be large rotations, which lead to span unseating mechanisms and to significant failure modes of bridges. So this is the initial concept. When we design a bridge, we have to have the seismic actions lower than the resistances. So bridge engineers utilize isolation devices such as viscous dampers or bearings. So this damper actually dissipates the energy through viscous behavior, and bearings dissipate energy through high theoretic behavior. We can increase the resistance, but by increasing the resistance, at the same time we increase the stiffness of the bridge, which the bridge is not necessarily safer than the previous one, than the previous design concept. This is not straightforward in structures of dynamic loading, because the reduction in the period, and we may attract, in that case, larger seismic loads. This can also be probably applies to bridges under wind effect, under wind loading. The seismic isolation, the idea of isolating a bridge against seismic loads seems to be a very good idea, actually. It provides flexibility to the structure, so the initial structure without isolation would be up here, and this is the loading, the inertial loads. If you use isolation, the system becomes much more flexible, and the isolation reduces rapidly inertial loads. This is a great idea. At the same time, we may also utilize bearings high capacity, having high damping properties, high capabilities, and to even reduce further the seismic load. Yes, this is a very good idea. Bearings reduce the serviceability loading of the piers, the seismic loading, and increase damping. But a past earthquake showed that actually that was not a really good idea, because many bridges have failed during the 2011 Great Tohoku earthquake in Japan. Many bearings were found to have ruptured completely through elastomer and direct tension. So what happened there? A recent publication that was of mine in a journal showed that if we use double lines of bearings on top of the pier caps, then we have to receive a tensile movement. The bearings have to receive a tensile movement, and bearings are not designed against tensile movements. They're not designed against tensile loads. So these bearings have failed, and many bridges have experienced collapses, span acidics, and collapses. If we think in terms of serviceability of bridges, we will see that the bearings do need replacement after some years of the bridge service. Isolated bridge responds with increased displacement since it's quite flexible. And of course, isolated bridges are statically determinate bridges, and failure may lead to collapses. There are expensive devices, do bearings in very high prices because they also sell the knowledge and the experiments that have been done in order to produce such bearings. And of course, technology went further. Theory codes provide some checks against elastomeric bearings and sliding bearings, whereas at the same time the market can provide us with a few hundreds of different types of bearings. So the question is, did expansion joints cause more problems than they solve? That something like 10 years ago, I made a turn to the unconventional bridge design concept, and I tried to utilize earthquake-resistant abutments. Those are elements which were not supposed to be effective and active during earthquakes. So this is the idea. This is the conventional bridge, large pier sections, large foundations, and one abutment that is in fact only retaining the backfill soil. Well, the idea that was proposed and was published several times in journals was to provide high capacity external support, horizontal support, like this abutment, and reduce effectively the pier section, the foundation design, the foundation, and of course reduce the use of bearings. So I'm not going to go through all these abutments. You see here many different C-type abutments that have been published in the past. Several integral abutments here were used to minimize the seismic demand of bridges, and ideas on integral bridge construction methods, some new construction methods that will cover bridge spans up to 45 meters. We also went through shake table tests. Shake table tests are modeling in laboratory real seismic actions, real seismic motions. So that was a single degree of freedom that modeled the deck of the bridge, and there was a connector here that was modeling the resistance, namely the stiffness and the damping of the abutment. So how are abutments being treated in Eurocode or in other American codes like ASTO? If we use a C-type abutment, then the abutments are not considered to contribute at the seismic action. If we use integral abutment, Eurocode 8 Part 2 requires that the behavior factor Q equals 1.5 shall be used. So this behavior factor, which corresponds to the American R factor, is a factor that shows how much of the induced seismic energy can be dissipated by concrete sections, by the piers. So if that factor is close to 1, that means that the structure shall remain elastic. So we use integral abutment bridges. If we design integral abutment bridges, the bridge shall remain elastic, even though the piers are connected rigidly to the deck. This is the philosophy. They utilize either integral abutments, and Calans provides an equation that for the calculation of the horizontal stiffness of the abutment plus the backfill soil. And there have been quite a few studies on the semi-integral abutment concept, which is a stub-type abutment that is connected through a connector, which is in fact a hinge, to the pile cap and the piles, and this hinge in fact reduces effectively the bending moments of the piles, and so piles are not susceptible to fatigue loads, mostly to fatigue loads like bending loads and constrained movements and constrained shear stresses. What is the requirement of Eurocode for the expansion joints? So this is the expansion joint. It's the gap between the deck and the back wall. This wall is called back wall. So this expansion joint has to take into account, of course, permanent movements due to creeps and gets. Has to take into account 50%. This is a 0.5 according to Eurocode 1, and multiplied by the gradient of the uniform temperature gradient. This joint has also to take into account 40% of the seismic movement, 40%, and not the whole seismic movement. If we expansion joints against a total seismic movement, then probably the expansion joint calculation will show that we'll need something like 300 millimeters of expansion joints, which are very, very expensive, and these joints should be replaced several times during the life of the bridge, which means that the cost of the bridge will be increased rapidly due to the need for the replacement of these devices. So the result of the coach design, 1990 Costa Rica earthquake, the deck pounded on the abutment, no provision for this collision effect was into account during the design, and so we had a tremendously rotated abutment, which of course cannot be retrofitted, and there are some slight damages in past earthquake pounding induced failure of the expansion joints, and of course you can see here that the bridge might be seeing the traffic access, but the expansion joints would not allow the emergency vehicles to the bridge. These effects can effects be modeled in practice with finite element software. You can see here that of course we can model such effects. For example, this is a Plaxis model that was modeling such pounding force on an abutment with surface foundation. The model was verified by the SAP model. This is a SAP 2000 model. This is a software that is provided by Berkeley University. The final result for the permanent movement, the residual wall movement, was up to 262 millimeters, which means that the bridge is not accessible. So abutment and the backfill soil are not considered in the earthquake-resistant system of the bridge. There are several serviceability related issues, such as the constrained movements of the abutment, the ratcheting effect that has been addressed in the past by Virginia University, and the deck serviceability loading that was published several times by our team back in my previous university, in Aristotle University. And of course, the embankment soil is not a reliable material. Who is going to design bridge relying on the resistance of the backfill soil? So the initial thought when designing an earthquake-resistant bridge that will all incorporate the abutment and the backfill soil in the lateral resisting system was to compromise between serviceability and earthquake resistance. Serviceability requires flexibility, and earthquake resistance requires high capacity. And methodology, of course, is the typical methodology for designing and analyzing bridges against earthquakes, non-linear dynamic time history analysis, with acrograms reduced to Eurocodes 8 Part 1 response spectra, detailed modeling of the dynamic system, and comparisons in terms of displacements, bending moments, and shear actions of bridges to see if the new concept, the unconventional concept, is efficient. And a lot of information about non-linear analysis of bridges in this book, The Seismic Design and Assessment of Bridges, and you can also visit this web page that is the page of Work Group 11 that is supposed to provide essential knowledge on Eurocode 8 Part 2. And members of this group, the Work Group 11, including myself, have strengthened the UK Mirror Group to follow developments and to propose changes to the bridge part of Eurocode 8. So, it was utilized only the conventional C-type abutment. Nothing was done differently from the typical design. except the expansion joints. The expansion joints, in that case, did not take into account seismic movements. So the deck was interacting with this abutment, and placements between the typical case, which is the bridge with the large expansion joint, and the bridge, conventional bridge with a small expansion joint, was compared in terms of this, deck displacements. What found was that when abutment participates in the earthquake motion, then the bending moments may be reduced up to 25%, which means at the same time that we can design the piers with smaller cross sections, and we can reduce effectively the cost both the piers and the foundations.
Can I just clarify one thing?
Yes, of course.
We're not fixing both abutments, are we? Fixing one abutment, are we?
Both of them.
Both of them?
Both of them. It's not actually, it is not actually fixing. We provide an expansion joint between the deck and the back wall, but the magnitude of this expansion joint, the gap, is much smaller than the typical one, than the one that code requires. Okay, so there's an interaction between the deck and the abutment, and further to that, the backfill soil is activated because the back wall moves towards the backfill soil. So that was the idea, to involve the abutment into the seismic problem. Having recognized that displacements are reduced and the bending moments of the piers are reduced due to this interaction, the back wall was strengthened. Let's see what will happen if the back wall is a high capacity external shear key, high capacity external support, having a thickness equal to 1 up to 1.5 meters. So we did some analysis. I'm not going to go through analysis with MATLAB, but the fact was that the displacements were further reduced. The displacements were reduced up to 40%. Then we shed more light on in the unexploited process of the backfill soil, and we extended the deck slab of the bridge towards the backfill soil. And what was done after that was to restrain this slab, this continuity slab, into the backfill soil. So these piles combine flexibility with earthquake resistance. Why? Because the piles have quite small cross sections, so they are quite flexible, and at the same time we can also utilize expanded polyester layers just below this pile cap of the piles in order to increase flexibility of the piles to receive serviceability movements due to thermal effects. During earthquake, it is tied to the backfill soil, and as such, the displacements were found to be reduced up to 70%. This is a tremendously large reduction in seismic movements, which means that the piers might be very slender, and the level of safety of the bridge remains essentially the same, since bridges, the conventional and the unconventional one, which utilize this system, were designed according to Eurocode Part 2 in that case. Then the idea was evolved into an external stopper. We said, okay, the backfill soil is not a reliable material, so we have to provide very specific properties of the backfill soil in order to utilize the backfill soil. So we said, okay, there are many bridges that are adjacent to tunnels, so let's tie this bridge to the adjacent tunnel. And this was provided through an extended shear key having a quite large volume, and you can see here the shear key that is actually restraining the movements of the deck, both the longitudinal, the transverse movements of the deck during earthquakes. You can see here the response time history analysis of the deck, and of course this shear key has to take into account thermal movements. Expansion joints were left between the shear key and the foundation of the tunnel in order to provide space for the movement of the deck. The displacements were found to be reduced 75%, and it is that this key can be utilized not only in case a tunnel is adjacent to the bridge, but a concrete structure may be developed there, may be designed there in order to restrain seismic movement. So there are many different ways which are very helpful to avoid extensive use of bearings and large cross-sections for the piers. It was another idea that was published in the Journal of American Society of Civil Engineers, Journal of Bridge Engineering. We control the pounding forces. The deck actually collides on these high-capacity wing walls. The wing walls were strengthened in that case, and the wing walls transfer the seismic load to the foundation of the abutment. And you can see here that additional measures were provided to avoid sliding of this foundation. Displacements were reduced up to 35%. It is underlined that this bridge was a quite heavy bridge, airway bridge, and that the initial concept for the design of this was to apply heavy aeration, a combination of high damping rubber bearings and viscous dampers. So the conventional design without dampers was compared, and still the displacements were reduced up to 35%. If we want to control the dissipation through elements, we can utilize restraining walls. Of course, we have to optimize the design procedure, as these walls are expected to receive serviceability movement, and they should remain elastic during the bridge service, while respond in an elastic manner during earthquakes. In that case, displacements were reduced up to 67% when the stiffness and high-theoretic behavior of these restraining walls was taken into account. So the concept can be applied also in case we want to retrofit to strengthen a bridge against seismic loads. And in that case, the measures are even more effective due to the fact that we don't have to take into account creep and shrinkage effects. Creep and shrinkage effects have already been developed during the first 2 or 3 years of the bridge service, and then we can close the expansion joints, by very small expansion joints, and so the bridge may interact with an external system restraining the seismic movements effectively. So at the time, most of these bridges, you know that most of these bridges have simply supported spans, which means that there are expansion joints over each pier. So in that case, it was considered to be essential to connect the adjacent spans, and you can see here what was done. A cast in situ concrete slab was utilized to connect the slab of the adjacent spans, and at the same time, a cable restrainer was utilized to connect the adjacent I-beams, the pre-stressed beams, and this tendon, this cable restrainer, was installed on the level of the center of gravity of the deck cross-section in order to avoid secondary bending moments. So it found, after analyzing this quite old bridge built back in 1986, in fact, it was found that these measures were adequate to additional seismic loads. So the bridge is considered to be when the bridge was checked against the Eurocode's 8 Part 2 design provisions, the bridge was found to be adequate to receive the seismic loads. If we want to disrupt traffic, we can apply different measures, such as the ones I'm showing here. So what's done here was that instead of utilizing pipes, we can use external barred walls, the ones shown here with a green color, and connect the adjacent spans by these red lines that you can see here model. Those are new sidewalks, in fact, and you can see here what was the invasion on the sidewalk. So part of the sidewalk was replaced. A cast in situ part of the slab, appropriately reinforced, was utilized, and the new elements, the horizontal one and the vertical one, was connected through dowels with the existing part of the slab. So, as you can see, the middle part of the bridge is accessible, and the bridge was retrofitted without disrupting, without closing off the road.